Day 2 of this deals with properties of radicals, and let me turn on a grid here. Okay, so these are things that, when we say properties of radicals, are really things that we're using to simplify radicals. So let me kind of back up to a question. If I have the fifth root of 2 to the 6th power, which you might actually see as the fifth root of 64 and have to factor it down to 2 to the 6th power. You should have a sense that 2 to the 6th power is really made up of 6 2's all multiplied together, 5 of which could come out as a perfect fifth, leaving me with 2 times the fifth root of 2. And sort of an easy way to get at that is to look at this and divide. I know that 6 divided by 5 is 1 with a remainder of 1. So one whole group comes out with a remainder of 1 left behind. That's a little old school in terms of division, but it also means that if I have something large like the 23rd root of x to the 51st, then I can see how many groups of 23 there are in 51. There are 2 groups, so 2 groups of 23 come out, and the remainder inside is an x to the 5th. Now, if this isn't correct, I've forgotten to write the 23 in the pocket here where the index goes, and I will have to count off a small amount of points, or like a half point or a point, if I see that. This is the full correct simplified radical. Both of these, this solution and this, these are called simplified radical form. It's not the only form that you're going to see simplifications happen in, but it is what's called simplified radical form. Simplified radical form is something we're going to get into a lot in this chapter. Okay, so let's go to a more simplistic example of simplifications. Simplified radical form implies 3 things must be true. First, there is no perfect radical factor under the radical. We'll say no perfect radical factor in the radicand. Remember, radicand was a word that meant thing underneath the radical. And the other 2 are a variant of each other. There's no fraction underneath the radical, no fraction in radical, and no radical in denominator. The radical in the denominator thing will not be as huge of an issue in later math classes, but in this one, we do need to have the skill. So for instance, if I have 6 divided by root 3, I should be able to simplify that by multiplying the numerator and denominator by the square root of 3 over the square root of 3. Square root of 3 over square root of 3 is a version of the number 1, and I would get 6 root 3 over 3, which simplifies to 2 root 3. This is also valuable because if I wanted to approximate 6 over root 3 and I didn't have a calculator, that would be very difficult to do. But if I knew that that was equal to 2 root 3 and I knew that root 3 was about 1.7, then I could get an approximation of about 3.4. And I know that this is equal to about 3.4. And this is how math would have to happen back in the days before calculators, when it was just tables of values and you have to get approximations to be able to compute certain things. So this is all good and fine. That's review. This is not. If I have 6 divided by the cubed root of 3, okay, now we have an issue, because what I'm going to see a lot of people do is do the same thing they did up above and just multiply it by the cubed root of 3. However, if I multiply it by the cubed root of 3 over the cubed root of 3, that will not get me what I need because it's a cubed root. When I multiply these radicals, I would get the cubed root of 9, which is not a perfect cube. I need an additional 3 in here to give me the 3 3's to come out. And when I clean this whole thing up, I will end up with 6 cubed root of 9 divided by, and all of this groups together to become just 3. And so my final simplified form will be 2 cubed root of 9. I'm going to pause this for just a second. So your calculator actually has the ability to confirm that these are the same thing. If I hit Control division symbol and do a 6 over and I want to do the cubed root of 3, so that's button is right here, nth root, cubed root of 3. Hang on, and press enter. It tells me this is about 4.16. Now, I'm going to point out that this, I don't always like that it does that. I want to have more digits visible, so I'm going to make that the default here. And let's go back and do that operation again, and I get something that looks more like a decimal that I truly know it's an irrational form. Then I can do 2 times the cubed root of 9, so 2 times, and let's do that nth root again, cubed root of 9, and it tells me that they are the same thing. So even though your calculator, the TI Nspire CX, does not do simplified radicals, it can help me confirm that my answer is truly a correct one. So let's move on and do some more simplifications. 5 over the cubed root of 12. So cubed root of 12, kind of the silly way would be to multiply by 2 more cubed roots of 12, but the best way would actually be to express the denominator in a factored form. 12 is really 2 squared times 3. You should know that and be able to take a prime factorization of simple numbers. Cubed root means that every factor needs to have 3 copies present to get rid of it. I have 2 2's here, I need a single 2. I have 1 3 here, I need 2 more 3's. That way I have 3 of everything. Numerator, multiply by exactly the same thing. Clean this up. 5 times the cubed root of 2 times 3 squared is 18. And the denominator, a 2 comes out and a 3 comes out. So my simplified form is 5 cubed root of 18 all over 6. And that has a radical in the numerator. Let's show another example of something very similar. Let's say that I have 5 over the 7th root of 12. And let's see how this changes. So 5 over the 7th root of 12. Well, this is really just 5 over the 7th root of 2 squared times 3 again. But now because it's a 7th root, I need to have 7 copies of everything. I need 5 more copies of the factor 2, and I need 6 more copies of the factor 3. Numerator, I would need 5 more 2's and 6 more 3's. It's because whatever I multiply the denominator by, I'm going to multiply the numerator by. And so when I clean the numerator up, well, we're just going to leave it like this because 2 to the 5th and 3 to the 6th are going to be large numbers. And there's no real need to multiply that out. But the denominator is going to come out as a 2 and a 3, which multiplies together to become 6. So that would be a simplified form for that one. I'm going to challenge you now with this next one to pause the video, try this one on your own, 3 over the 5th root of 72, and resume it. And if you've resumed now, we have 3 over the 5th root of, I'm going to factor 72, 9 times 8, or 3 squared times 2 cubed. I know that I need 5 of every factor, which means I need 3 more 3's and 2 more 2's. 3 3's and 2 2's. So my numerator becomes the 5th root of, this is 27 times 4, or 108. I should always wait to draw radicals until I know how big the number is. And the denominator is just going to become another 3 times 2. And since it's 3 times 2, these 3's can cancel, and I would get the 5th root of 108 over 2. Once more, if you wish to verify this, you can go to a calculator and type in 3 over the 5th root of 72. Check that, and then now do the 5th root of 108 and divided by 2. And they are the same thing. So that's that's simplification. Let's summarize some points about radicals, or some true properties of radicals. So this is one property of radicals that we've discussed, or we kind of alluded to. The nth root of a times the nth root of b is equal to the nth root of ab. Radicals can multiply. Property number 2. the nth root of a divided by the nth root of b is equal to the nth root of a over b. This actually happens when you see things like this. If I have the square root of 1/27th and I want to simplify that, well, that can be broken up into the square root of 1 over the square root of 27, or 1 over 3 cubed root of 3. And then when I multiply this by cubed root of 3 over cubed root of 3, I get the cubed root of 3 over 9. Sometimes you may have to go the other way, where I have a radical 2 over a radical 8, and the easiest thing to do is not to rationalize that, it's actually to make it a single radical, radical 2/4, which is radical 2/8, which is radical 1/4, which is 1/2. So at different times you may want to split it up, at different times you may want to bring it together. Okay, let's continue some more examples of some simplifications. And this is going to pull on some skills from yesterday. So the first one is 1 over 2n cubed under a radical. Before I do anything, I want to check, simplify this denominator radical first. So let's make this 1 over the nth root, n cubed, square root of n cubed, so n square root of 2n. And we did this thing yesterday where I checked what would happen if n was negative. And if n was negative, I would have 1 over the square root of a negative, which I can't do. But if n is negative here, in my simplified form, I'd have 1 over a negative square root of negative, which I also can't do. And believe it or not, that actually matches. So I don't need to worry about any absolute value or anything. It actually means that n could not be negative. It can't be negative because if I took the square root of a negative number, I don't get a real number. So that happens in both of these. No worries at all. But I do want to simplify this 1 over n root 2n. I want to get this expression out of the denominator. So what I'm going to do is multiply it by a root 2n, and I get root 2n over 2n times n will give me n squared. And again, if n was negative, we'd have a negative underneath a radical, and that matches everything I've seen from the previous two simplifications. Let's go to number 9. Let's do the 6th root of x to the 12th, y to the 6th, z to the 18th, a to the 24th, and b to the 9th. Okay. X to the 12th 6th rooted is x squared. If x was negative, then a negative to the 12th would give me a positive, but then a negative squared is also positive, so we're okay. Y to the 6th 6th rooted is just y. If y was negative, y to the 6th would be positive. If this y was negative, the y would stay negative, so I need to force it to be positive. This is because the 6th root of y to the 6th is the absolute value of y. Let's keep going. Z to the 18th, 6th rooted, gives me z to the 3rd. Another uh-oh. If I had z to the 18th, 6th rooted, equaling z cubed, the left side, if z was negative, would make it positive. The right side would not. So I need to force that to happen, which means I need to force that z to be positive. Let's stick the 3 out a little bit. Okay, a to the 24th, 6th rooted, gives me a to the 4th. A to the 4th will be positive no matter what, and so will a to the 24th. We're okay. And finally, b to the 9th, 6th rooted. Well, I know that that means that a single b can come out, and then I'm going to be left with 3 b's inside, b cubed and 6th rooted. Well, I don't need to worry about any absolute values there because b could not be negative. Right here, if b was negative, then we'd have an issue with a negative underneath a 6th root, which I can't have a negative underneath a 6th root. There is no 6th root of a negative number. The same thing happens here. We're okay. So this is a good problem type to study to kind of figure out what is really going on with these absolute values and when do I need it and when don't I. Number 10. In number 10, we're going to simplify just something a little bit more simpler than number 9, root 18m squared. Go ahead, or sorry, wait. Yes, root 18m squared. Go ahead and pause the video, do this, and then come back. And you're back. Root 18 is easy. That's 3 root 2. So 3 is going to come out, and a radical 2 is going to stay in. I know I have an m coming out, so I have a root 2. But, again, I have the square root of m squared. So if you did not put the absolute value, shame. You need to. If m were negative, m squared would destroy that. So I must manually destroy that negative as well by putting the absolute values around that. Number 11. This is going to be another chance for you to practice this. 6, 100, x to the 6th, y to the 12th, z to the negative 18th. And I'm going to put a different direction here. We're going to assume all bases are positive. Now, if you see that assumption, you do not need to put absolute values at all, because if all bases are positive, then we really aren't going to run into that issue. So in this case, 100 factors into 10 times 10, which factors into 2 squared times 5 squared. That 100 is never coming out of that radical. X to the 6th will come out as an x. Y to the 12th will come out as a y squared. And z to the negative 18th will actually come out, and this should be really logical, as z to the negative 3. Because a negative 3 times itself 6 times is going to be a negative, or negative 3 added to itself 6 times is going to be a negative 18. It is true that we can think about this as division, negative 18 divided by 6. And I still have the radical 100. Let's not forget the little 6 in there. That's needed because it's not a square root, it's a 6th root. And then if I want to really make this look good, we're going to move this z to the negative 3 down to the denominator and have it listed like that. Now, if I did not assume that all bases are positive, would you know which ones of these would have absolute values? X to the 6th here, but then it just becomes an x, which doesn't destroy negatives. I would need it on that. Y to the 12th becomes a y squared. That's no big deal. Still both destroys negatives. Z to the negative 18th. The z to the 18th is going to get rid of negatives, but z cubed is not. The z would need it. So if we did not assume all bases are positive, then we would see that we still need the absolute values around the x and the z. I'll pause for just a second again. Okay, and resume. Some other problem types that happen here include things like when I have a square root or any sort of root across pluses or minuses. So I have 100 square root of 100x squared plus 100y squared. That one is tricky. People are going to want to make it be 10x plus 10y, which is totally wrong. You can never distribute an exponent across addition and subtraction. What I can do is I can factor a 100 out and get x squared plus y squared, and the square root of 100 is 10, but that x squared plus y squared is going to stay inside. Likewise, some other things that can happen would be problems like this. Evaluate if x is equal to 3 and y is equal to 4. And if I do something like the square root of x to the negative 2 plus y to the negative 2. So what I end up with is, I know 3 to the negative 2 is 1/9 and y to the negative 2 is 1/16. But what's going to happen is somebody's going to tell me that that is 1/3 plus 1/4, which is completely incorrect. You have to follow order of operations and add these up. If I add up 1/9 plus 1/16, I get 16 plus 9 over 9 times 16. I'm actually not going to multiply the 9 times 16, and you'll see why here. I am going to add the 16 plus 9 to get 25, but 25 over 9 times 16, now everything is multiply, divide, and I'm doing a square root. That's 5 over 3 times 4, or 5/12. Okay, I'm going to do some example types from stuff that you would see on the worksheet. You're going to have a worksheet that has lots of these types of problems. Oh no, I did plenty of those. We're good. I'm just going to cut it right now. Enjoy.